can see why by using the Poincare disk model. A small triangle looks pretty ordinary, but as you make it bigger, the angles start to become smaller and smaller. Eventually, all those angles go to zero, because all these lines intersect the disk at 90 degrees. Now, these lines are infinitely long, but because of the geometry, the area is finite. In the same private letter, Gauss wrote, "All my efforts to discover a contradiction and inconsistency in this non-Euclidean geometry have been without success." Just like Bolyai, Gauss had found that this geometry seemed thoroughly consistent. He named it non-Euclidean geometry, a name that stuck. It describes geometries where Euclid's first four postulates hold, but the fifth doesn't. But Gauss decided not to publish his findings for fear of ridicule. This aversion to a different kind of geometry should at least be a little surprising, because there is one other geometry that we should be very familiar with, spherical geometry, since we all live on a sphere. On a sphere, straight lines are parts of great circles. These are the circles with the largest possible circumference. On Earth, the equator and circles of longitude are examples of great circles. And we can use this to see how straight lines behave. These lines seem to go in the same direction, but as you keep extending them, you find that they intersect, once and then again on the other side of the Earth. And this will always happen for any two great circles, because they must each have the largest possible circumference. So in a sphere, there are no parallel lines. Gauss had long been fascinated by spherical geometry. He was also a geodesist and frequently took measurements of the Earth. In the 1820s, he was tasked with surveying the Kingdom of Hanover to help make a map. As part of this survey, he climbed the mountains near Göttingen. With the help of people situated on other landmarks, they were able to carefully measure the angles of several triangles, which would then be used to determine the position of one place relative to another. As a reference for the survey, and to help determine the roundness of the Earth, they also precisely measured the angles of a large triangle formed by three mountains. But for all of Gauss's romantic notions of taking measurements on top of mountains, he was not the kindest correspondent. When Bolyai received his hero's response, he was devastated, believing that Gauss was trying to undermine him and steal his ideas. He was so embittered by Gauss's response that he never published again. In 1848, Bolyai had to endure another hardship when he found out that Russian mathematician Nikolai Lobachevsky had independently discovered non-Euclidean geometry, several years before Bolyai had published his 24-page long appendix. In 1832, 9 years after he discovered his strange new universe, he published his findings as a 24-page appendix to his father's textbook. Extremely proud and excited about his son's work, Farkas Bolyai sent it to perhaps the greatest mathematician of all time, Carl Friedrich Gauss. After careful examination, Gauss replied a few months later, "To praise it would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years." Years earlier, Gauss had wandered a similar path. In 1824, he wrote a private letter to one of his friends in which he describes discovering a curious geometry, one with paradoxical and, to the uninitiated, absurd theorems. For example, Gauss writes, "The three angles of a triangle become as small as one wishes, if only the sides are taken large enough. Yet the area of the triangle can never exceed a definite limit." In other words, you can have a triangle that's infinitely long, but the area is finite. You can see why by using the Poincare disk model. A small triangle looks pretty ordinary, but as you make it bigger, the angles start to become smaller and smaller. Eventually, all those angles go to zero, because all these lines intersect the disk at 90 degrees. Now, these lines are infinitely long, but because of the geometry, the area is finite. In the same private letter, Gauss wrote, "All my efforts to discover a contradiction and inconsistency in this non-Euclidean geometry have been without success." Just like Bolyai, Gauss had found that this geometry seemed thoroughly consistent. He named it non-Euclidean